Hi everyone, I am Allison, and today we're going to talk about the paper titled On the Convergence of Atom and Beyond. I am here with my teammate Lee Minju. This is what we're going to talk about today. First, we are going to talk about the notations and the optimization setup. And second, we're going to introduce the common methods that were classic in optimization problems, such as the stochastic gradient descent, eta grade, and atom. And third, we show that atom does not converge by providing a counterexample that atom diverges. And fourth, since that atom does not converge in every scenario, we propose a new method with a convergence guarantee. And since a new method is proposed, we also want to fix atom, since it is such a great framework. So we propose another algorithm, atom NC, which is fixing atom. And six, we proved that first atom does not converge, and our two proposed methods do converge by some empirical results. Now, let us go over the optimization setup and the notations. S subscript D superscript positive represents the set of all positive definite matrices, and F denotes the feasible set, and the projection operator projects the point Y onto the feasible set F under a transformation determined by matrix A. The term alpha t denotes the step size at time t, which is adjusted as alpha over square t, where alpha is a constant scaling factor. Ft is the loss function at time t evaluated at point xt. Now finally, RT represents the regret at the end of T rounds. It is the difference between the cumulative loss incurred by following a sequence of decision XT and the cumulative loss of the best single decision X within the feasible set F in hindsight. The optimization setup has two rules. The first one, we should ensure that the feasible set has bounded diameter d infinity, and the second one is that we should ensure the gradient of the loss function at each time step is bounded. And also by ensuring that the regret converges linearly, we are implying that the model converges to optimal. And this is because that the average regret per round vanishes as t goes to infinity, meaning that the algorithm's average loss becomes indistinguishable from the average loss of the best fixed decision. And the algorithm converges to the optimal solution x star if the problem is convex and well posed. Thus, RT equals OT is a formal guarantee of the convergence in online optimization. And for the following, we are going to use this trait as the proof to prove that atom is not converging or the proposed method is converging. In this slide, we present the general iterative framework optimization, described as algorithm 1. The algorithm begins with an initial point x1 from the feasible set F, a step-size sequence alpha t, and a sequence of functions phi t and psi t. For each iteration t from 1 to t, we first compute the gradient of the loss function, and combine the gradients using the function phi to calculate m, and weights of the gradients with psi giving vt. Perform a gradient step to update xt plus 1 hat using the formula xt minus alpha t over square vt times mt. Finally, project xt plus 1 back to the feasible set using the projection operator. Functions phi t and psi t determines how the gradients are combined and specifies the weighting of each gradient. A stochastic gradient descent is a special case of the optimization framework. In SGD, phi t is just the previous step gradient, and psi t is 1, which is the gradient is not weighted at all. And therefore, xt plus 1 is basically xt minus the gradient direction and with the step size alpha t. Such aggressive update often leads to poor empirical results, and therefore the first weighting method was proposed, eta grade. Eta grade modifies the optimization framework to adapt the learning rate based on past gradients. Here phi t equals gt, but the psi t adjusts based on the cumulative sum of the squared gradients, represented as diagonal elements of the g square over time step t. The update step then becomes xt minus 1 equals xt minus alpha over the square of all the diagonal elements of the gradient square. Eta grade performs well when gradients are sparse, but it can be too aggressive when gradients are dense and non-sparse. ADAM, a short for adaptive momentum estimation, introduced an exponential moving average of past gradients and squared gradients. The function in ADAM, the moving averages, are computed as 1 minus beta 1 with and over an exponential decaying factor beta 1 and g.
In this section, we are going to discuss the issue of non-convergence of Adam algorithm. The reason lies in the fact that algorithms using exponential moving average tend to have the problem where the learning rate is non-increasing over time. Classic methods like stochastic gradient and eta gradient do not have this issue. Therefore, in certain simple problems, using eta may result in non-convergence of average grades. Mathematically, this can be expressed as a description in Theorem 1. To prove Theorem 1, we design a specific problem ft. Here's a problem definition. We can see that the output of ft determined by the value of x and t. If t mod 3 equal to 1, then the output is cx. Else, the output of ft is equal to minus x, where c is greater than or equal than 2, and x belongs to the interval from minus 1 to positive 1. Here we try to think about a problem. Since c is greater than or equal than 2, and there is a cycle every 3 steps. So the impact of time t, that's mod 3 equals to 1, is greater than the other 2 steps. Means that c is greater than minus 2, the adding coefficient of x with the other 2 steps. Therefore, we have known that regret is a summation of ft of x over t. So when x is equal to minus 1, the regret is minimized. And here is a gradient of function ft. Before we go into the proof, let us first define the variables involved in executing the Adam algorithm. Since beta 1 is unrelated to the learning rate, it is defined as 0 for convenience, and define beta 2 to 1 over 1 plus c squared. And then alpha t defined with alpha over root t. And we set x1 to be 1. Notice that the projection of algorithm is Euclidean or projection on the interval from minus 1 to positive 1. Next, we have a property with this problem. For all t belong to non-negative integers, x3t plus 1 equals to 1. To prove this property, we use mathematical induction. The general steps are as follows. First, we check that x1 equals to 1 is holds. Then, check x3t plus 4 holds under the assumption that x3t plus 1 is equal to 1. And x1 equals to 1 is defined in the setting of the algorithm we mentioned in previous slide. So the first step is check. And in step 2, we first derive the equation from x hat 3t plus 2 to x hat 3t plus 4 by adding algorithm. And just like x minus learning rate multiply gradient, here alpha over root 3t plus 1 multiply epsilon is learning rate. and C is a gradient of f3t plus 1. The others follows the same pattern. Next, we observe that x hat 3t plus 2 is greater than 0, because it is equal to 1 minus this term, and this term less than 1. We can also deduce that x hat 3t plus 3 and x hat 3t plus 4 are also greater than 0. Then we further analyze x hat 3t plus 4. Due to projection in Euclidean space onto the interval from -1 to +1, so the projection can be changed to the minimum of x hat 3t plus 3 and +1. At this point, we consider two cases. If it is greater and equal than 1, it is easy to see x3t plus 4 equals 1. Else if x hat 3t plus 3 is smaller than 1, here we bring in the equation of x3t plus 3 and x hat 3t plus 2. And to make these all greater than 1, we have to check that the left turn is less than the right two turns plus together. If it is holds, then we can say that x3t plus 4 equals 1. Fortunately, we found a variable that lies between the two, and this inequality comes from. Here, we mentioned previous slide, and to see this 2 is greater than alpha over root 3t plus 1 multiply 1 minus beta 2. Here we change 3t plus 2 and 3t plus 3 to much greater number, 2 multiply 3t plus 1. And in this equality, we use a definition of beta 2. Here we give a reason that beta 2 c squared is equal to 1 minus beta 2. And thus, x3t plus 4 is equal to 1, and also completes the proof for the property. Finally, using the property and the definition of the ft, we can see that for every c steps, the regret has a lower bound of 2c minus 4. Hence, we know that the average regret will not converge to 0. 1 is not the only case where it applies, but even with the additional constraints of constant beta 1 and beta 2, or in a high-dimensional convex problem, the Adam algorithm can still converge to non-zero regret. That is to say, we have to reset the constant beta 1 and beta 2 every time we use the algorithm, and that costs a lot of time and troublesome.
So after all these introductions showing that Adam is not correct and diverges, we are finally introducing a new exponential moving average algorithm, AMS grid. By giving a temporal related sequence beta 1 and a constant beta 2 satisfying beta 1 over the square root of beta 2 being less than 1, the regret has the following bound. And the step by taking maximum between v hat t minus 1 and vt actually ensures that the learning rate is non-increasing. Let us prove theorem 2 for the first part. Lemma 1 is given a positive definite matrix Q and a convex feasible set. Let U1 and U2 be the projected points of two arbitrary points Z1 and Z2 onto the feasible set. We have the property that the distance between U1 and U2 induced by Q square is no greater than the induced distance of Q square between Z1 and Z2. And recall that in Lecture 8 we learned about the non-expansiveness of projection operators, and here's the screenshot of it. That is, the distance between the projected points is no more than the distance between the original points, and lemma 1 can be considered as a special case of such theorem. Let us consider the inequality we have from lemma 1, and since xt plus 1 is projected back onto the feasible set, let xt plus 1 be u1, and z1 is xt xt minus alpha over the square root of vt times mt, which is the updated point before projection. By expanding the L2 norm, right here, we obtain that the optimality gap induced by matrix V to the power of a quarter between xt plus 1 minus x star is no greater than the optimality gap induced by Vt to the power of a quarter times xt minus x star plus alpha t squared times v to the power of negative a quarter times mt squared minus the dot product between mt and the optimality gap times a coefficient of 2 times alpha t. And we can further expand MT according to its own definition, where MT is the weighted sum of MT minus 1 and GT. And what we want is the upper bound of the dot product between GT and optimality gap XT minus X star. And therefore, by rearranging the terms, we have the upper bound of GT and XT minus X star right here. And we can further expand it by Cauchy-Schwarz inequality, which is expanding these two terms with its own norm. By the property of convexity, we derive that the suboptimality gap is no more than the dot product of the gradient and the optimality gap. And we can utilize this fact to find the upper bound of the regret, because we can observe that the suboptimality gap, summing all those suboptimality gaps, is necessarily the definition of the regret, and we can use it to derive the upper bound of the regret.
Recall that we have derived the inequality of the regrets in the first part. And this part we pick this term and then analyze the upper bound of it. Here, use the recursive method to prove. Before starting, we have to know the closed form of MT and the oops on T for the following proof. Here, we just recursively derive the equation of definition of exponential moving average. Next, try to solve the closed form of this term. We begin with deriving the last element of the summation. And after multiple steps, we got the upper bound of the last elements. Here, since n as gradient will take maximum of oops on t minus 1 and then oops on t each time. And this place use the closed form of nt and the oops on t just mentioned previous slide. Next, we use Cauchy-Schwarz inequality on the closed form of nt. And then we use definition of beta 1t less than and equal than beta 1. And thus we can remove the product here. And here use the upper bound of a geometric series. And here is because each xi is divided by the sum of all y. And thus this term will less than the xi divided by each yi. And the less inequality, we use a definition of the gamma. Next, according to the last elements of the summation, we expand all the other t to get the closed form here. And these two equalities just change the order of the summation and the variables. Then here we change to t is because t is less than the oj here. And here we use upper bound of a geometric series. And the last equality, we use the upper bound of a harmonic sum. Just briefly mentioned, we can see the image to know why the upper bound of harmonic sum is 1 plus log t. After solving the closed form, we got the upper bound with complexity of the square root of 1 plus log t. and multiply the gradient known. And thus, we complete the second part of the proof. In the rest of the proof, we combine the results of the first two parts, and use the scale of a telescope sum to derive the upper bound of the regrets. And here we plot these two terms and get the upper bound. The inequality here is since beta 1 t less than beta 1. Next, we change the learning rate to alpha t minus 1 over vt minus 1. That is because learning rate is non-increasing over t. Last inequality, we just take from the second term of time t plus 1 to here. And it is also the same as the first term of time t. So it will multiply by 2. And thus we get the upper bound of these two terms plus together. And here we can exactly bring the result of the second part to this term and get the upper bound with the complexity of square root of log t. Keep deriving the equation. We pick the first term of the summation over t equal to 1 and then put it here. And we move the second term over t equal to 1 to the second term of t equal to 2. And we do the same step each t. Means that for each t in the summation, the second term will have vt change to vt minus 1, xt plus 1 to xt, and alpha t to alpha t minus 1, beta 1 t to beta 1 t minus 1. And in this inequality, we plus and then minus the same variable here, and try to make this and this term together. And the other two terms we derive the upper bound. Then we can see that two terms we hope together left here, and the other two terms upper bound left here. And then we multiply this term with a number greater than 1 by 1 over 1 minus beta 1. And then here, we'll change to 1 minus beta 1 squared. Since here change to 1 minus beta 1 squared, then we found that these two terms are become the same. And thus we plot it together by multiply 2 and get this term here. And the last equality, we change the representation of the value of each dimension of epsilon t head. So here, and here, and here, have the summation of I over 1 to d. Next, we use the diameter as upper bound of distance x minus x star, and change distance with diameter bound d infinity. Here is the inequality after changed. And then we see this summation. And found that by using telescope sum, except the second term over t equals 1, and the first term equal to big T in the summation. The other terms will be removed by minus itself. Like, if t is 2, we have root epsilon 2i head over alpha 2, and t is 3. We have minus root epsilon head 2i over alpha 2 here also. So these two can be removed by plus together. And the other terms is also removed by doing the same thing. Finally, we put it in the inequality and get this upper bound. Therefore, we complete the proof of the theorem 2. After the proof, we can see that the complexity of the ANS gradient could be faster than the big O root dt if the summation of the epsilon is much smaller than the root d and the summation of the gradient known much smaller than root dt, which means ANS gradient considerably better than stochastic gradient. And see the theorem too. Even we use a modest momentum decay on beta 1, it still have the complexity of the root dt.
The paper also proposed a method to fix atom, and we name it as the atom NC. By an increasing scheduling of beta 2, atom is fixed without changing the structure. The fixed version of atom can also ensure convergence by giving the time-varying sequence beta 1 and beta 2 satisfying the two conditions as the following. The first condition bounds the effective learning rate and ensures that the second moment updates are sufficiently large to counteract any pathological scaling behavior. And the second condition ensures that the inverse of the learning rate is non-decreasing, and therefore the learning rate is non-increasing. Let us set beta 2t be 1 minus 1 over t. Plugging into the recursion of vti leads to the closed form of the squared sum of gradients over t. By setting beta 1t to be beta 1 times lambda to the power of t minus 1 and replacing vt with its closed form, the regret bound can be further simplified and can have the following reinterpretation as here. The regret bound of stochastic gradient is the big O square root of dt, and the regret bound of fixed atom, which is atom NC, can be better when the magnitude of the gradient is load smaller than the square root of dt. So following the suboptimality gap derivation in section 4.1, let us borrow that equation as equation 3. And we can first study the term alpha t times the L2 norm of Vt over to the power of negative a quarter times mt. Let us break the summation into 1 to t minus 1 plus the last term when t equals to capital T. Plug into the closed form of mt and bt, and expanding the square term and put the square gradients on one side. Since beta 1k is smaller than beta 1 for all k, we can replace the product with beta 1 to the power of t minus j. And since the sum of a limited geometric sequence is always smaller than its infinite sum, we can replace the sum of the geometric sequence by 1 over beta 1 and move it outside of the summation since it is invariant. From the condition in the theorem that the square of its long summation divided by alpha t is greater or equal to the summation of all the gradient square divided by a constant, let us replace the denominator with the summation of the gradient square divided by a constant zeta, which is replacing this whole thing with this whole thing with this one, and taking the summation away from the fraction since the denominator is invariant to t, summing through all those time steps, and replaces the geometric coefficient beta 1 to the power of L with infinite sum. The final inequality is derived by plugging in the inequality that replaced the ugly fraction with a clean L2 norm of the gradient. Plugging in the result of the previous slide into the regret bound and extracting the first term of the summation, we derive the second inequality. And by plugging in the matrix V and use the L infinity norm, we have obtained the stated regret bound. In the end, we will go over the experiments that were conducted in this research. As mentioned in section 3, the authors use a simple example to showcase the divergence of atom, and in the experiment part, the authors aim to demonstrate similar symptoms through empirical results. We examine the regret with respect to time, as we can see that the regret does not converge asymptotically to zero, and the left two figures are the figures for online setting, while the right is for stochastic setting. The y-axis of the two figures on the right is the value of xt, which is the solution that will give you the minimum regret, and obviously the value is negative 1, but from the figure we observe that AMS-GRAD converge to negative 1 almost immediately, while atoms stick to the value of 1. And AMS-GRAD also demonstrated superior performance on logistic regression and a one hidden layer neural network. The MINS dataset is used in the top row, classifying a 784 dimensional image vector into 10 categories. By setting beta 1 to 0.9 and beta 2 is chosen from 0.99 and 0.999. The figures in the bottom row are the training loss and testing loss with respect to the iterations for CFAR-net using the CFAR10 dataset, where inputs are images with shape 32 times 32, and we can also tell that AMS-GRAD also surpassed Atom in this scenario. One key findings or little flaw that we found is that this paper did not conduct any empirical results on Atom NC, and I think that this will be a major part in our final project. And this is our project. Thank you so much for your patience and attention.